Our next statistical phenomenon that we need to be careful about is called the multiple testing problem or multiple comparisons. Let's say you're testing something that doesn't actually have any effect, a new medicine that doesn't actually work. What percent of the time will you end up rejecting the null hypothesis and deciding that it does work? Well, that would be a type 1 error, rejecting the null when the null is actually true. And what's the error rate on that? It should be alpha, which is usually 5%. So about 5% of the time you're going to make a discovery even if there's no discovery to be made. Like anything important in life, there's a webcomic about it, so let's go see that. And I'll let you kind of read this. I'll scroll through it slowly. P was greater than 0.05, so they did not find a statistically significant link. They're trying all the different colors here. Whoa, look at that. P less than 0.05. And then what's going to happen? Okay, so hopefully this teaches us a lesson that if you try 20 things, and even if none of them really would work, on average, one of them will look like it works. So that's a pretty important thing to keep in mind. In education, if you are looking at which topics did students improve on from pre to post, and look at each topic individually, that could be a lot of topics. And even if no one really improved, just by chance, you'd probably see 2 improvements out of 40. In economics, people have looked at the relationship between how much debt a country has and how much growth it has. You'd think the more debt it has, the less it's going to grow. Even if there's no relationship, if you test there's about 200 countries, you're going to see a, quote, statistically significant relationship in about 10 of those countries. In computer science, it's easy to program a simulation that tries a bunch of different things and do a bunch of hypothesis tests. Once you get it programmed for one, it's easy to replicate it, and then you're going to have lots and lots of false positives. And in biology, there's something called a gene chip or a microarray that has 20 to 50,000 different little DNA or RNA strands on it, and you're going to end up doing a hypothesis test for each one of them, of course in an automated way. You're going to get a lot of, 5%, but 5% of 50,000 is quite a lot. So what do we do about this problem? There's an old method called Bonferroni that just says, well, if I have an alpha of 0.05 and maybe I'm doing 10 tests, then I use 0.005. I divide alpha by the number of tests. But it turns out that makes it too hard to make actual discovery. We lose statistical power that way, so no one likes to do that. There are these fancier methods that we don't have time to look into in our class, but you can Google them if interested. When I asked the computer science department what should students learn about in stat360, some people mentioned these, that at least they should, computer science students should learn that they exist. So that's the problem of multiple comparisons or multiple testing. Let's go look at the next big statistical issue. That's called the publication bias or file drawer effect. Let's say a bunch of researchers are doing studies on whether some particular medicine helps some common disease, and they get these following p-values. Now I'm just generating these randomly, just uniform between 0 and 1. Let's copy them and paste them back as values. So this first researcher does a study, gets a p-value of 0.66, writes up a paper, submits it to a journal, and the editor looks at the p-value and says, that's not a statistically significant result. And so the editor says, why are you bothering me with non-significant results? Go away. And then the next researcher does their study and writes it up with a p-value of 0.2 and submits it to this journal, and the journal says, why are you bothering me with non-significant results? Go away, I'm not going to publish your paper. Now, if you're the third person who has studied this, and you pretty much know that this tends to happen, that if you send in a paper with non-statistically significant results, the journal's just going to reject it and say, why are you telling me that X does not help Y, or at least you have no evidence that X helps Y? Only tell me the interesting things when you make a discovery. Are you even going to write up your paper and take the time to submit it? No, you're just going to let it sit on your hard drive or in your file drawer if you have an old-fashioned paper file drawer. Um, so this researcher won't even bother writing up the results and submitting them. So that's called the file drawer effect, or that publications are biased toward only publishing statistically significant results. We might ask, how is this different than the Jelly Beans comic we just saw? There, we kind of believed the result when it happened, which is like publishing it, but also they were still doing each individual test and kind of thinking about publishing it. Here we aren't even thinking about sending it in, so there's no public record that it happened. But by the time you get down here, wouldn't it have been nice for this researcher to know that none of these previous people had found a statistically significant result? Maybe that would have saved this researcher some trouble. They could go research some different medicine. So it's kind of inefficient for science to not be publishing these, quote, negative results, because knowing them could save other people some time. So this brings up another paper that's really interesting called Why Most Published Research Results Are False. It's because journals only tend to publish statistically significant papers, and a lot of those are ending up statistically significant just by chance, and we're not even seeing the ones that people tried that didn't end up statistically significant. In medicine specifically, there's something now called a pretrial registry. So if a company wants to test 10 different medicines, they have to say ahead of time that they're going to test them, and then they have to report to the pretrial registry what happened with each of those, so we're getting a full scientific record of what happened and not only seeing the successes.